Let's say we want to do the square root of 8. The square root of 8. All right, so how would you go about doing that?
You take the 8 and you find the factors of it. So you would go like 4 and 2, do like a factor tree.
Uh-huh.
And then you factor the 4.
Okay.
And you circled the amount of like doubles you can take out.
Okay.
So you can take out
like that?
2, and then you like, I guess, can circle like in another color, the one that has to stay in because it doesn't have a double. So it would be like
this.
And then and then you multiply the. Wait, no. You just take out a 2, and then it'd be like 2 root 2, right?
Right. Where's the so? Let's say you have this blue 2 and this blue 2 and this yellow 2. Okay, so and you said the answer is 2 root 2. 2 root 2. What color is that 2 and what color is that 2?
Green and red.
Those aren't options. What are you talking about? I said yellow and blue.
Sorry.
If I get it, yeah, green. So you're saying yellow and blue, right?
Yeah.
That's correct. All right. You kind of stole my thunder. I was going to teach you that. All right, let's do a harder one. Okay, so I'm going to improve upon that a little bit, I guess.
Okay.
So let's do the square root of... that's kind of a ridiculous number. Hold on. 336. So we'll do the square root of 336. So the first thing you want to do is, how you said you do your factors? Okay, so always go with the smallest possible factor you can do. So for example, if you're doing 100, right, you don't want to do 10 and 10.
Okay.
It's better to do 2. And you want the small number, the small prime number, to be the one on the left. You want to keep all your small, tiny primes nice and tidy on the left.
Okay.
Easier to keep track. Because sometimes, we make these factor trees and we do all this crazy stuff, and then we're like circling, and then we like forget a number over here. It gets like lost in the mix. But if you do it like this, then it's really organized. Okay. So we're going to take what out?
2.
2. So 336 divided by 2, 168. What are we going to cut 168 by?
2.
2. All right, 84. What are we going to cut 84 by?
2.
2. And I love when it's 2 even numbers like that. What's half of 84?
I don't know.
What's half of 8?
4.
What's half of 4?
2.
We could do it again. So 2, and then what goes here?
2.
And then
2 and 1.
And then here we can't do 2, so then we do 3. Then what goes here?
7.
7, and that's it. It's all prime. Okay. So then we circle our buddies. So there's buddies right there. There's buddies right there. And these guys they don't have buddies, right? And then one guy gets shot, killed. This other guy goes out. You have a 2 out. This guy, dead. This guy comes out. And then the other ones that are not, that don't have buddies, they just stay here. And that's 4 root 21.
Okay.
And you always know if you did it right because you can just do this number times itself times the number on the inside, and that should take you back to the original.
Okay.
So try that. So you should do, or we can do it right here. So we can do, what times what?
4 times 4 times 21.
4 times 4 times 21. Okay, that's a plus, not an equal. Let's just totally edit that out of the video. 336. And we start off with 336. You get that?
Yeah.
All right, let's say you're going to do the square root of 567. The cube root. The cube root of 567. All right, so how do we do that?
So we have to first do like a factor tree of that. So I'm trying to think. 11 plus 8.
It's odd, right?
Yeah.
So we're obviously not going to try 2.
Mm-hmm.
It doesn't end in a 0 or a 5, so which can't we? So what numbers get eliminated?
3. Oh wait, I was.
So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so 1 doesn't even get to play, and then are we even going to try 2?
Mm-hmm.
No. Okay. What about 3? Yeah. I mean, if you get to use a calculator, just try in a calculator.
Mm-hmm.
If you don't get to use a calculator, then you add these numbers up and what?
Yeah, you see if it's divisible by 3, which is 18, so it would be.
It would be. Okay. And 4 is a possibility. Oh, and then when do you even do a 5 check?
Wait, couldn't you not even do 4 because it's not an even number?
That would be true because anything that 2 can go into.
Yeah. So
2 can go into 4 can go into, right?
Yeah.
Yes. And these guys are just weird. Well, not that one, but this one. So like 8 got eliminated, 10 got eliminated,
Mm-hmm.
6 got eliminated,
Mm-hmm.
4 got eliminated. What about 5 and 10?
10, it doesn't end in 0.
Right. What about 5?
Because it doesn't end in 0 or 5, it can't be 5 either.
Right. All right. So we divided by 3. All right. So 567. Here you can do it. 567 divided by 3 is
189.
All right. What are we going to divide that by? It's odd. Let's just try 3.
Okay.
Okay, go
Because it
ahead.
ends in 9. 63.
Yeah, not necessarily because it ends in 9, just the fact that it's odd. It may not work. See, not all numbers end in 9. Like,
Well, because didn't we were saying that like when you add it up or like when the last number is divisible by 3, because 9 is divisible by 3, you know it's 3.
no.
What when you add this up, it's 9 and 9, which is 18, and 18 is
That's correct, yes. But not the fact that it's 9. Like this wouldn't work.
Yeah. Okay.
Because you have to add them all up.
Mm-hmm.
Okay. But a lot of times it just works. You feel like winning the lottery when it does. Okay, so 63. All right. 63. And then what are we going to divide that by?
3.
All right.
21.
Okay, so 3 and 20. And you see how I'm not going to do like 9 times 7.
Uh-huh.
Right? I want down to the small. I want all my primes on the left.
Okay.
All right, and then right here.
You can do 3 again.
Mm-hmm. And then that's definitely not true. Okay, that. All right, now what do we do?
We circle our 3s, our triplets.
All right. And then gone and gone. That comes out, right?
Mm-hmm.
All right. So 3, and then what's left behind?
Another 3 and a 7.
Yeah. So then you have a cube root, and then a 3 times 7, right?
Mm-hmm.
Okay. And I suppose you could check this by doing this times this times this times this.
Okay.
Try that. So 3 times 3 times 3 times 21.
Yeah.
All right, cool. So that's our basic lesson. Now let's talk about if you have something like the square root of 25 over the square root of 81.
So you would first find the square root of 25 and then the square root of 21, and then you divide the two.
Okay, so what do we got?
5 and 9.
Okay, so 5 over 9.
Mm-hmm.
All right. What's the difference between this, like this whole setup right here, and this?
This you like divide first and then you do the square root. But that's like you find the square root of each number, then you divide.
Actually, nothing's different between the two.
Oh.
They're exactly the same.
Okay.
So you can, a lot of times, if you get like a problem like this,
Mm-hmm.
you can separate it. So like, I don't know how to do that, but I know how to do this. Like at least I know how to deal with the top part.
Mm-hmm.
You see, so sometimes it's easier, like if you have this type of deal, like actually not like that type of deal, like what's an example? Like the square root of 50 over 2. All right? It's kind of awful to do this. The square root of 50 over the square root of 2. Mm-hmm. That's a hassle. Or I can just divide, and what do I get?
25.
25. Then I can just do the square root of 25.
Okay.
And that's easy. But I can do all the work on this one and still get the same answer. Mm-hmm. Okay, so here, this is the way I want to approach this problem, because at least I can do the square root of one of them if I split it up. Mm-hmm. If I don't split it up, it's just an absolute nightmare. Okay, so then on top, what do I get?
5.
Okay, and then the bottom is root 17. And then this is considered like math illegal. So how do you fix it?
I mean, my guess would be you put in a calculator and get some decimal.
No. So they want an answer like 5 root something over something with without the root. They want it like that.
That's weird.
Yeah, because so the reason why it's math, there's a couple things that are math illegal. One is having a root in the denominator. It's just like, it's like bad math grammar. Another thing that's not really illegal, but it's just bad math grammar, is like having a negative on the bottom. Mm-hmm. You can just put it on the top. You can just write that as like that. And then the other thing that's, let me think. Stuff like this, like they don't want it like that either. Okay, so basically you just can't have a root in the denominator. Okay. All right, so what you do, even though it's technically this is right, it's just improper. So you want to multiply top and bottom with the denominator, with the exact denominator. Like that.
Oh, so it just becomes 17.
Where?
Down there.
Perfect. Yeah, so 17. And then on the top?
5 root 17.
5 root 17. All right, and then the other one is if you have like 3 over 3 plus root 5. Okay, so that's improper. So the way you deal with this is you multiply top and bottom by the conjugate of this. And what the conjugate of this means is it's the same exact thing, but opposite sign in the middle. So what is this with the opposite?
3 minus root 5.
3 minus root 5. And then the same thing on top, because what is 3 minus root 5 over 3 minus root 5?
1.
1. So you're multiplying a fraction by 1 and changing the value of the fraction. And the reason why you're multiplying it by the conjugate is because if you FOIL it open, you're going to get a middle wipeout. So 3 plus root 5, and then 3 minus root 5. So let's do our FOIL. So what's our first?
9.
What's our outside?
3 minus root 5.
So it's this times this, right?
Oh, yeah, 3 minus root 5.
Wait, no, because you're doing this actually. You're doing that times that.
So it'd just be negative 3 root 5.
Yes.
Okay.
So it's negative. So negative 3 root 5. All right, that's our outside. What's our inside?
3 root 5.
Mm-hmm. Positive 3 root 5. And then what's our last?
Negative 5.
Great. Okay, and what's going to happen right there?
Cancel.
Cancel. You're going to get a middle wipeout. So you know how we did FOIL? Well, when you're dealing with conjugates, you actually don't need to do that part. You just do first and last. So when we're over here, we put all of this in a thought bubble. So when you want to work out the bottom, first and last. So what's your first give you?
9.
What's your last give you?
-5.
-5. See, no more root. Root's gone.
Yeah.
And then, all right, so on the top, what do you get there?
9 minus 3√5.
Perfect. 9 minus, so you have that, and you have an invisible one right here, and then that and that. So 9 minus 3√5. Okay. And so you end up with 9 minus 3√5 over 4.
Okay.
And that's that. If you have like a 3 instead, then you can factor out a 3 from the top. So if you pull the 3 out of the top, then what would you end up with?
3 minus 1√5 over 3.
And then what can you do?
Over 1.
Over 3. Because we only pulled the 3 out of the top.
I thought you were like canceling all out.
Well, then after that you do this.
Okay.
Do you see that?
Yeah.
So this is just, if I put it back together again, it's 9 minus 3√5. So this top is exactly the same as that top, and this bottom is the same. But now I can do this. Okay. Couple more things. What is root 20 times root? I really would like to pick easier numbers. Root 7 times root 3.
Is it root 21?
It's root 21. Why?
Because because they have like, it's the same thing. Kind of see it as like 7x times 3x. You can like, because they have that same thing in common, they can like multiply together, and because they're both like the roots, they can like multiply the inside together.
Yes, but 7x plus 3x I can do.
Yeah.
Right? And 7x times 3x I can do.
Yeah.
But can you do root 7 plus root 3?
No.
No. So I kind of think of it like, it's just kind of a weird way to think of it, but if they have the same tail, so I think of, there's probably a better way to think of this, but this is my weird way. So let's say you have like you have some number here, and you have like a tail, like a fox tail, okay. And you have plus 4 with the same exact tail. All right, the same tail. Then you can add them together. All right, so what is that? What is that going to be?
7 tail.
7 foxtail. All right. But if you have like 3 foxtail plus 4, I don't know, whatever the heck that tail that is, can you add those together?
No.
No. But if you're multiplying, then they can still talk to each other, right? So when I get kind of confused, I just think of the root as like a tail. So like you have to have the same tail to add, but you don't have to have the same tail to multiply. So these guys can't talk to each other through addition, right? So like, but they can through multiplication.
Yeah.
Right, so that's root 21. But then what about root, like 3 root 7 plus 10 root 7?
Yeah, because they have the same thing.
Same tail, bam. So what's that answer going to be?
13 root 7.
13 root 7. And then you don't like, multiply the roots together and stuff. But what about 3 root 7 times 3 root 7 times 20 root 2?
Yes.
Okay, what would this answer be?
60 root 14.
Yeah.
Really?
So the buddies talk to the buddies. So it's the non-tail times the non-tail and the tail times the tail.
Okay.
So it's 60 root 14. And that would be the same thing as like 3x squared w r to the 4th times 12x to the 7th w to the 8th and r. All right, so we're multiplying. So just the buddies multiply with each other. So what is that going to be?
3x to the 9.
Buddies.
Oh, wait,
buddies.
wait, 12 times 3.
36.
36 x to the 9. And then w to the 9. And then r to the 5th.
R to the 5th. Okay. That's it.
Okay.
I think that's everything as far as roots go. If you're dealing with letters in roots, so we should talk about that, I guess. So like, let's say you're doing the square root of a to the 4th. You know what that would be?
You still like factor tree?
You don't have to. It's you could. There's like a trick.
Wait. So you can know that there's like imaginary 2 there.
Good.
So you can see like how many times can the 4 go into, like how many 2's are in the 4?
Yes.
So you take out an a squared.
Correct. So you take out the 2, and that's that.
Mm-hmm.
All right. But what if you had like the cube root of a to the 19?
You do like, I think my teachers taught me something like, is it like you put the 19 over the 3 and you like see how many times it can like divide?
Yeah.
But it can't.
So pretend like you're in 4th grade and you're doing this problem, and then we're going to have like the little r up there.
Okay.
So then what would this be?
It would be 5 remainder 3.
No,
it would be 6 remainder 1.
Good. 6 remainder of 1, right? So then your answer is a to the 6, right? And then root a to the 1.
Okay.
So your remainder is the one that's left behind, and however many times it goes into perfectly is what comes out.
Okay.
And that's it.
Perfect.